Good evening. How are you? Happy Saturday evening. Uh, so yeah, we're doing some partition function here. Let's go grab the whiteboard here. Okay. So what's going on here is that if a number is sufficiently large, that I mean, as big as 10, you have a lot of ones, right? So until it hits the wall on the left, okay, this pattern is fixed, be it 100 or 1000, okay. As long as you don't hit the wall on the left, the way it increases, it's exactly the same, all right. So that's something we just discovered, like in the last episode, which is quite interesting, okay. So but once you start to hit the wall, like on the left, like this, then things become icky. Okay, so yeah. Okay, so and so that's the top down approach. Bottom up approach. Um, yeah, at least two of this. It we know what this is. What this is. Okay, it's just n divided by two, one. Okay, so yeah. It's like you have river, fresh water, right? And then you have salty water out in the ocean. But when the fresh water meets the ocean, sea water, it kind of like become like chaotic, right? This turbulence and whirlpool, and that's kind of what we're seeing here, right? Yeah. And we are missing one partition here somehow, and I don't know where. And yeah. So yeah, our algorithm have some bug. We, we missed four numbers. Okay, so yeah. Oh well. Yeah. So about like half a year ago, last year's October, when I went to trip to San Diego, California, yeah, I was studying partition function, and I still have that written down on my notebook. But the way I approached back then was using strict lexicographical ordering. All right, so here we are not doing that. Okay, we are doing something else. Okay, so um, so let's take a note that ordering doesn't have to be lexicographical. Okay, so yeah, we just need to find algorithm to enumerate this exhaustively. Yeah. So the algorithm we want to find is exhaustive list of partitions given on input number. Okay, so that's the problem we are solving now. Let me grab some jacket. It's kind of chilly. So okay. Let me grab a coke. Okay, so yeah. All right. Okay. Okay, so yeah, so last year, yeah, I did discover some interesting recurrence relationship and interesting structure by lexicographically ordering the order partitions. And it was a good approach. Okay, I did learn a lot, discover some. Okay, so but I didn't quite find that closed form formula for partition function. Right, so yeah, that's why we're taking different approaches this time. Okay, so all right. Why do we miss 1, 2, 2, 5? Try to understand this. Okay. Yeah. Yeah, so we are not going to order this lexicographically, okay? So that's the confusion. Yeah. Because we are not using the same algorithm as I did like half a year ago. 1, 2, 2, 5, the way where it belongs is actually 1, 2, 2, 5 here. 1, 2, 2, 5. Well, 6 is donating 1 to this second one, okay? So 1, 2, 2, 5. And 1, 3, 3, 3. Yeah. Right. 4 donates 2, so okay. All right. Whew. Yeah. Oh, now it's getting hot, so let me take off my long pants. Okay. 1, 2, 2, 5. All right. Okay. Let me create myself and look up partition of 10 because I just don't cannot find what am I missing. I have no idea. We are missing one still. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 41. We are missing one. Okay, so give me 1 second. Let me check with my friends already, okay? Yeah. Partition of 10. Oh boy. Hey. So yeah, Oasis, they are fantastic website, okay? So they do have this partition table for 10. So let's check it out one by one, okay? So oh boy. This is gonna take a while. Okay. So you have that, that, 2, 2, 2. Okay, so they use somewhat different ordering. Right, interesting. And 3, 1, 1, 1. 3, 2. 3, 2. And 3, 2, 2. And 3, 2, 2, 2. Then you have 3, 3. 3, 3, 2. I think that may be what we are missing. 3, 3, 2. Okay, okay. 3, 3, 2, 1, 1. All right. 3, 3, 2, 1, 1. 3, 3, 2, 1, 1. 3, 3, 2, 1, 1. 3, 3, 2. 1, 1, 2, 3, 3. Okay, 1, 1, 2, 3, 3. Okay. 1, 1, 2, 3, 3. Okay. We found them all. Okay. So our algorithm yeah, we're gonna tweak it a little, okay? So for donate one to two, so that's how you got one, one, two, three, three. Okay, all right. Okay, all right. So yeah, I mean there can be many different correct algorithms to enumerate correctly all the partitions, but different algorithms use different ordering. All right. Last year I used lexicographic ordering. Okay, so partition function, partitions, enumeration of partition. There are many many different way to order them, and using different algorithms. Okay, and we are trying a different one. Okay, because depending on your logic, your enumeration method, uh, you may be able to find some closed form formula for it. Okay, all right. Now, but we need to get this algorithm straight first. Okay. Mm-hmm. So the algorithm is this. When a number is bigger than some previous numbers, then at least by two, then this bigger number can donate one to that previous number. It still preserves that uh, non-decreasing order, like monotonic function. Okay, it's not, it's stay the same or go up. Non-decreasing function, monotonic. Okay, so we are preserving that monotonicity. Make sense? When we donate to the left. Okay, so that's the blueprint, the bird's eye view. That's the big scale concept of this algorithm. All right. Minor details, yeah, we'll figure that out. All right, and but let's take like 5 minutes break. Okay, so yeah. Okay, let's take 5 minutes break. Okay. Interesting problem, right? So our good old friend partition function. Okay, so uh, it is fairly important. Okay, so and also it gives us some training. So it is worthwhile to investigate this. Okay, all right. Yeah. Okay. So what we are doing nowadays is recreational mathematics. Okay, we may not contribute to mathematics very much. It doesn't matter. We're just having fun, right? Yeah, that's what matters. Okay, recreational mathematics. Okay. Let me grab my blanket. What matters is that we are legitimately happy. We are having fun and we are not doing anything wrong. We are happy, but anything that we do here is legal and moral, ethical. So that, oh, I call that a success. Okay? Whether we make contribution to mathematics or not, they got enough good mathematicians out there. So yeah. All right. So let's play a game. Okay, with numbers. The rule of the game is this: any game has a rule or a set of rules, right? That's what a game is. Like you have poker, bridge, you have blackjack, and all these card games. They have different set of rules, right? That's what makes a game a game. The name of the game, right? Is the rule, set of rules. Okay? So, the rule of the game here, partition game, okay, in this particular algorithm is this. You have 1, 1, 1, 1, 4, right? So, the difference between 4 and some previous number is 3. Okay? But, we're gonna only donate 1 by 1. We're not gonna donate 2, although we can. Actually, we cannot. But here we can, right? You have 5, and there are a lot of ones to rich man, poor guys, rich men on the right, like conservative people, okay? And then you have poor people, liberals on the left, okay? So, this rich conservativist conserves is donating some money to poor leftists, okay? Only in humanology we can connect between connect dots between mathematics and politics. Nobody else can do this. Okay. So 5 is donating 1 to the 1 right before itself. So it's neighbor, right? So it becomes 2 and 4. Okay? Now 2 cannot donate 1 because to previous one because it becomes 2 and 1. That's decreasing order. Oh, we don't do that. So that's another rule, all right? It has to be non-decreasing order. It could stay the same from left to right, or it can go up, but it cannot go down. Okay, so that's the rule. Okay. So 2 cannot donate to 1 because it becomes 2 and 1, and it's decreasing order, right? Oh, we don't allow that. And but 4 is very rich guy, so he can donate 1 to 2 to make it 3 3, or he can donate 1 to the last one here, so it becomes 2 1 1 1 2 2 3. Okay. So let's mark this. So these two guys, it has the same origin. Okay. So this guy. I need lighter pen. I need a lot of colors. Well, how about that? Perfect, right? So, I'm kind of excited. Okay, so five donate to 1, right? And yeah, that's the only thing you can do, right? And then here, 4 donates to 2. And there, um, 4 donates, well, we don't really have to think of that way. Yeah, 4 can donate to the 1, but uh, also we can think of it another way. 3 donates to 1, okay? So that's why it becomes 2, 2, okay? So, and that's easier way to think about it, okay? I'm not sure if it's necessary to think of this like skipping generation, skipping donation, like grandfather donate to grandchild, so to speak. I'm not sure if that's necessary. Okay. Uh, Actually, it is necessary. That's why we missed 1, 2, 2, 5. Okay. 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 All right. Yeah, that's fine. And here you have 3 donating to 1, right? Yeah. Okay. 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 Next group. 6 donate to 1, so you come to 5, right? 5 donate to 2, okay? And if 5 donate to 1, it becomes this guy. Alright, so let's see. And 4 donate 1 to 1, so it becomes this. 3 donates to 1, so it becomes this, and then uh, 3 donates to 1, okay, so alright. 7 donates to 1, 6 donates to 1. Mm, it shouldn't be here. It should be. So 6 donate to 3, and then 6 donate to 1. So 1, 2, 2, 5. Or 3 donates to 1, okay? Yeah. Yeah. 1, 2, 5. Okay. So I want to come up with the easiest algorithm, right? Yeah. We may need to reorder this a little bit. Okay, so we just need to be thorough and exhaustive in this enumeration. That's all that matters. Okay. Okay. And I want to design an algorithm. We want to design an algorithm that avoid redundancy. Okay. Uh, so we want to design a very efficient algorithm. For, okay, one algorithm that works for all these different partition groups, right? Um, we have 10 partition groups. Okay. So first group has 10 numbers. Second group 9 numbers. Third group 8 numbers, and so on. Okay. Okay. We are almost there, right? We just need to think about this a little bit. It's a puzzle, mathematical puzzle. All right. So okay. Well, let's come up with an algorithm that may generate some redundancy, but because we can always, at least in computer programming, we can always have hash table and to check whether this already exists in our set or not, right? So mathematical formula, yeah, we'll table that for now. Okay, let's get the algorithm straight and then, okay. Uh, let's take 5 minutes break, all right? And we're gonna grab another whiteboard and come up with some algorithmic design. Okay, all right. and we'll make use of this example. Okay, so this is a P10 set, partition of 10 that contains four numbers. Okay, and there are 1, 2, 3, 1, 2, 3, 9 ways to do that. Okay, so we focus on this guy. Okay, all right. That takes 5 minutes. Oh. Ah. Okay. So we're gonna grab new whiteboard, okay? Let me put back this long pants because it's chilly. Okay. All right. Whiteboard hunting. Uh, Well, we had to erase our good old friend Goldbach triangle, okay? Because it didn't quite work, right? Yeah. Another one of failed approach, so it's about time to erase this guy. Alright, so no problem. Because we can always reconstruct this if we need to. Okay, so erasing doesn't do any harm. Alright, so just if we need to redo this, just minor inconvenience, right? Yeah. Yeah. Difficult to erase because it's been here for by now like 2 months. More than 2 months. About 2 months. Okay, so oh, look at this. Yeah, I do have this spray, washing spray, but yeah, I would rather just use brute force. Okay. Good enough. Alright. Now we have whiteboard. Okay, so we'll start with 1117. Okay, so we have 1117. Alright. Now it's gonna be more understandable to you. Okay, I do step by step. Okay, so 7 between 1 and 7, the difference is 6, which is more than one difference. When difference is only 1, you cannot donate. Why? It becomes decreasing order. Okay, so but when the difference is 2 or bigger, then you can donate. Right? So, and when 7 donates, it donates to the closest leftist. Alright? So, it gives 1 to this guy. So, 1, 1, 2, 6. Okay? Now, from here, there are multiple ways to donate. Okay? So, let's do bifurcation. Okay? So, first, 6 can donate to 2. And it becomes 1, 1, 3, 4, 5. Right? Or 6 can donate to 1. Then it becomes 1, 2, 2, 5. Okay? And that's all you can do. So from here to here. Yes, let's construct a graph. Okay, so there's no more donation, other kinds of donation possible. Okay. And our rule, you can only donate 1, not 2. Okay. Yeah, because that it becomes too complex. Okay, so and then this guy can donate 1 to 3 or 1. Okay, so to donate to 3, it becomes 1, 1, 4, 4. Donate to 1, 1, 2, 3, 4. Okay? That's all you can do. This guy can donate to 2, and that's all you can do. There's no other way. 1, 2, 3, 4. Oops. Redundant. There's redundancy, so we cross it. Okay? This guy. We always start from the left. Okay, so big number, the leftist big number. Okay, yeah, that's this third digit 4. Okay, so if it donates, you may trifurcate. I don't know. So 4 donates 1. Okay, so it becomes 1, 2, 3, 4. Oops, it's already there, so we cross it, and How about the second 4? So that's all it can do. Second 4, no, it cannot donate anything. Because if the second 4 donates, it becomes decreasing order. Okay, so alright, so that's that. And how about 1, 2, 3, 4? 3 can donate to 1, right? So becomes 2, 2, 2, 4. Okay. Can 4 donate to 1? Yeah. Two, two, three, three. Okay. Is that all we have? Well, here. We can do some more here. Okay, so uh, 4 can donate to 2, so it becomes 2, 2, 3, 3. Okay, so how many do we have? 4, 5. There we go. 9 of them. Okay, so this is correct algorithm. Okay, yeah, there's some redundancy checking, but I tried to come up with an algorithm that does not have any redundancy. But so far, this is best I can do. All right. Yeah. Let's think about a better algorithm where it does not generate any redundancy. Okay. Hopefully it's possible. I don't know. So in partition problem, yeah, different people use different algorithm and different ordering and different grouping, right? The way we group here is our partition group has the same number of digits. I mean same number of numbers. We have 4 numbers here. Okay, so yeah. Because each number in a partition, it can be more than 10. Okay, or yeah, so it doesn't have to be single digit. Okay, so okay, is it time to take a break yet? I don't think so. Okay, how can we get rid of redundancy? Hmm. Iki. Oops, made a mistake. 2233. We already have that. So we are missing one again. Let's see what we are missing. One, three is missing. Okay. How did that happen? 1333, huh? Okay. How do we make 1333? So what? Oh, okay, okay. Yeah, it does trifurcate. Four can donate to two. Okay, okay. Actually, it should come before that. So four donate to two, so that 1333, and then four donate to one, and then it's 2233. Okay. All right. Hmm. Ah, boy. All right. Well, let's. Okay, we found out some algorithm is not very efficient because it contains redundancy, but whatever. Yeah, we'll get back to this algorithm, okay? Because let's try something else, okay? Okay, let me see. let's say that some bigger number, okay, one, 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 many ones, blah 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 blah, okay, and then it ends on seven, okay. We have plenty of ones, okay, and let's see how it behaves, okay. So the way it breaks down, okay, and then you have all the left blanks, they're filled with ones, okay. So you have 2 6, right, and then because it's donating, and here we are hitting the brick wall on the left, okay, because there's no more ones, trending ones, okay. So yeah, that's kind of difficult, right? So let's assume that we have a lot of ones and see how it behaves. Okay. Okay. So you're 117, right? 117, but 7 is like 1 plus 6, okay? And you're kind of distributing the 6, okay? And 1126 is like 1 1 1 1 and then 1 and 5. Like 1 plus 1, 2, 5 plus 1, 6, right? So we're kind of partitioning 6 into 1 and 5. 6 is 1 plus 5, right? Okay, so that's what's going on behind the scene. Alright, so. Okay, 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 okay. And partition of 6. Oh, I see, I see. Let me. You take 5 minutes break, okay? Let me grab my cell phone and. My guess is this, okay? This guy, the group 4. No, it's. Yeah, P10 4, okay? P P10 4. Partition of 10, group number 4, meaning you have 4 numbers to add. How many ways are there to express 10 as summation of 4 numbers? So that's the partition 10 4. That's that, okay? My guess is that this is same as partition of 6. It's a conjecture, okay? And we'll see if it's correct or not. So let me grab my cell phone and look up the partition table, okay? So, yeah, it's probably correct conjecture, okay? So yeah, and 6 is 10 minus 4. How convenient, right? Okay, interesting, all right? last year in October, I also made a lot of discoveries. Okay, it could some of them are rediscovery because later on I realized somebody else already discovered it, and but some of the discoveries is it could be unique, first in time. Okay, so yeah, we're just having fun with mathematics. It doesn't really matter whether it's brand new or second-hand discovery. It doesn't matter. Okay, so right. Yeah, we are making very good progress here. Alright, so ooh, it's chilly. Okay. Okay. How interesting. Yeah, I was wrong. Partition of 6 is 11. Okay, not 9. Well, I don't know why, but let's investigate, okay? Yeah. So, the 11 partition of 6, huh? Okay, well, kind of puzzles me. Let's see. Because, okay, maybe I was wrong, huh? Okay, that's fine. You have 2233, okay? 2233. But behind that, you can break it down to 1111 plus 1122. Okay, so yeah, which is partition of 6. Okay, so we are missing two of them. Okay, because there are 11 partitions of 6, and here we have only 9 partitions of 6. Let's enumerate. Okay, all right. We're gonna need another whiteboard, unfortunately. Uh, shoot. Well, let's just do it right here. Okay, so There are only 9 of them, right? Yeah, so, okay, so this turned out to be false. Okay, and let's understand why it is false. How interesting. Okay. I'm gonna start drinking, okay, because it's too dry otherwise. Okay. Let's slow down a little bit, okay? Yeah. Where's my favorite drinks? I have California red wine and the Birch Tree Spring Shoot vodka here. So, yeah, let's just relax. I'm very excited about this. Okay, so. Our good old friend partition function. Okay. Good, good. Alright, so this guy's false. So here, you have 6. Here, 1 and 5. We just subtract 1, 1, 1, 1. Okay, then see what's left. 2 minus 1, 1. 5 minus 1, 5. Okay, so 1, 5. Here, 2, 4. Here, 1, 1, 4. You know what I'm doing, right? Okay. 1, 1, 4. 1, 1, 4. Here you have 3, 3. Here, 1, 2, 3. Here, 1, 1, 1, 3. Here, 2, 2, 2. Here, 1, 1, 2, 2. Nine of them. Alright, so some partitions of 6 are missing. 2 of them are missing. Okay. Okay, 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 okay. Because we are confining the partition of 6 of length 4 or less. That's why. Okay, so 2 of them, what are missing? Well, of course, we have 1, 1, 1, 1, 1, 1, right? And next, yeah, our algorithm, right? To add the last 2, 1, 1, 1, 1, 2. Those are the two missing ones. Okay. All right. Well, that's fine. Okay. So P 10 4 is equal to P 6 1 plus P 6 2 plus, we don't need this anymore, so P 6 3 plus P 6 4. There we go. In general, P n x, okay, is equal to sigma I from 1 to x P n minus x I. Well, at least we discover something. It's a recurrence relationship, okay? So in partition function, a lot of recurrence relationship is known, right? And I did find some like last year, and now we found this. Very good. Whew. But recurrence formula is not closed form formula, unfortunately. Okay? Yeah. But it is something, okay? Okay, we found something. Very good. Excellent. Yeah, that's good. Right? Yeah. This makes sense. Let's see if this formula works. Okay, let's make some other example. Uh, we don't need this anymore. So, partition of, according to this formula, P10 right, is equal to P, you subtract it, right? P9 1 is equal to dot 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 is equal to P 1 1 is equal to 1. Okay, so yeah, it works in this case. How about P10 2? According to our formula is equal to P 8 1 plus P 8 2. Yeah, that's not correct. So something's wrong with our formula. Okay, so this is demoted back to a conjecture. All right, so and it's turned out to be wrong. Okay, so it works sometimes, doesn't work some other times, and because this is not equal. All right, with P10 2. Oh, actually, I'm sorry. Yeah, this is correct, and this could be correct. We will see. Well, let's look at this guy. Well, we don't know it's correct or not. Okay, so we know this is 5. Okay. Well, let's see what right hand side looks like. P8 1. Yeah, that's 1, right? Plus P8 2. How many ways are there to express 8 as summation of two integers? That's 4, which is 5. It is equal. Okay, okay. Okay, good. How about P 10 9? Well, that's equal to what? P 1 1, which is 1. How about P 10 8? Is equal to P, subtract, okay, so P 2 1 plus P 2 2. Oops, Yeah, yeah, yeah. Okay. I guess it works then. Huh? Okay, well, great. It works. Yeah. Can we prove this? Yes. I think we should to make into a theorem. Alright? We know it works, okay? Now it's time to formally prove it, okay? So, we're gonna prove this verbally, informally, okay? Because we don't want to spend too much time here, alright? So, okay. I just explain it to you, okay? Formal proof, I rather leave it to you or to other people, okay? So, we are looking at 1117, okay? So it's a partition 10 4, right? And 1117 is equal to 1111 plus 6, like 0006, okay? Now, there are different ways to partition 6, and partition 6 with length 1, I mean one number, or partition of 6 that has two numbers, three numbers, and four numbers, okay? And you're gonna order each partition in non-decreasing order, right? And then you add 1111, okay? So that's the partition of 10 with length 4. That's the informal proof. It's not a proof, but that's the concept behind this formula. Okay, and yeah, it is correct formula. Okay, I'm not gonna prove this. Okay, yeah, you can use mathematical induction, right? Yeah, but you have two variables here, so we proof we'll leave it to professional mathematicians. Okay, so we are amateurs, all right? So I am. Okay, so okay, all right. Now, so we found the recurrence relationship for partition function. Um, yeah. By the way, this is one kind of restricted partition. Okay, it's a subset of partition. All right. So yeah, it's common method in partition number theory, partition theory. Okay, so restricted partition. Okay, so it's very common technique. Okay, so categorization and subsetting the subdividing the partition set. Okay, so very common technique. There are many different kinds. Okay, so partition function itself. Oh yeah. Partition function P of n, okay, or P of n is equal to sigma I, well, we'll use j from 1 to n, p n j, okay. So which is equal to, using our formula, sigma j from 1 to n, so it's double sigma, okay, sigma I from 1 to j, okay, we substitute j for x, p n minus j I. So it's not a closed form formula, but it's a recurrence relationship. Well, at least we have one, right? We found one. Okay, good. And this means we can build a pyramid, array of numbers. Okay? Just like Pascal's triangle. Okay? I know this because I've been studying this systematic enumeration method, like pyramid number and like Euclidean triangle, and yeah, I did study a lot of that. So I recognize, yeah, we can build a pyramid here, and we'll do so. We call it partition pyramid. Okay? Yeah. Maybe somebody discovered it already. Okay? We'll look it up. Okay? But let's take 5 minutes break. Okay? So, whew. Very good. Okay. Let's take 5 minutes. I'm gonna take off this long pants and let's relax. Excellent. We build partition pyramid, alright? So. Yeah. Okay. So, ooh, let me clean my glasses. So we're gonna build something like Pascal's triangle, and we call it partition triangle, Euclid's triangle. But it could be three-dimensional object. All right. So if it's three-dimensional, then we call it partition pyramid. Or it could be four-dimensional. I don't know. I'm not sure about the dimensionality of that array of numbers. I'm not sure. So, but we'll go ahead and construct that. Okay. So, yeah. I'm so excited. Okay, my hands are shaking. Oh boy. Oh, let's not shake my hands. Oh, but when I'm excited, oh boy. Today is a good day. Okay, we found something of some significance here. Okay, so yeah, I mean partition number. I looked up in the Wikipedia, and there's Young's diagram, Farrell's diagram. Yeah, okay, so and it's not the same as this. Okay, so those diagrams they're just a graphical representation of the partition sequence. Okay, so it's not the same as this. Okay, so just like Pascal's triangle. Okay, what we're gonna try is to build partition numbers, right? Uh, by just adding a bunch of numbers with some specific rules, just like Pascal's construction of Pascal's triangle, because we have recurrence relationship. All right. Yeah. So Pascal's triangle is take advantage of the recurrence relationship of binomial coefficient, right? So we'll do something similar. Okay. So. Because well, I need to write this down, right? Okay, I write right here. Yeah, this notebook traveled to San Diego with me. Okay, so when I was studying like partition function, so okay, I just write down the result. Good. In mathematics, the simpler the better. All right. I mean, complex like equations like Ramanujan equation. It's beautiful, right? But in mathematics, the simpler the better. Okay. Um, how about Mr. Einstein's the field equation? But it's wrong equation. Okay. His entire theory of general and special relativity. It's time for them to go. Okay, because they are wrong theories. All right. Yeah. But we did disprove both here, about several months ago, right? But because I'm not famous, nobody pays attention to what I have to say. Okay, so okay. But yeah, if I become famous, then I will say again about I will demonstrate to the people that yeah, the disproof of Einstein's relativity theories. Okay, all right, that later. Okay, so it goes like this. Okay, P61 can be further broken down into like 5p1, blah blah blah, right? P62 can be broken down to P41 plus P42. P63 can be broken down into P31 plus P32 plus P33 and on. Okay, so it has this branching pattern, right? Yeah. Okay. Yeah. So it's gonna be big triangle, right? Yeah. We need to grab a whiteboard. Okay. So let's see. Let's go and look. And I'm getting chilly again. So this is how I spend my time. Okay. Putting on, taking off clothing 100,000 times a day. Because I'm very sensitive about temperature. That's why I never get sick. Alright? Because I know how to regulate my temperature very well. Yeah. Let me grab my socks. Okay. What can we erase? Found one. Okay. Whew. I'm not sure what we discovered today has been discovered by some other people or not. I don't know. Alright. And to us, it's irrelevant question. Why? Because it doesn't matter whether it's brand new discovery or rediscovery. We don't know and we don't care. Alright. We just have fun. Okay. That's what we do. It's getting chilly. Oh. Okay. Now it's too hot. Oh, just kidding. Okay. So first, let's build some foundation. Okay, so because we don't know how to draw that partition pyramid yet or triangle, not yet. Okay, so let's just take step by step. Okay, so P of P of 3 is equal to P31 plus P32 plus P33. Okay? And we know this guy is 1 and this guy is 1, okay? So we only need to do this, okay? So P32 is equal to, uh, oh, sorry. So you subtract, right? So P1 1 plus P1 2. Yeah, okay. So our formula is not quite perfect, huh? Okay, okay. Yeah, we need to refine our formula. All right. So because you cannot do this, okay? The superscript should be always equal to or less than subscript. All right. So that's the rule. So we need to refine our formula a little bit. So we have Pnx is equal to sigma I from 1 to x, but it's not up to x. It's all till, uh, well, we should impose some condition here, okay? So, uh, n minus x and I, okay? All right. We'll refine this, all right? But this is the condition it has to satisfy. Okay. Oh man, it makes my head spin. Okay, so, but this is easy. Okay, so it's just that uh let's break it down. P 3 2 is equal to P 3 minus 2 and then 1 plus 3 P 1 2, but you cannot do that, okay, because superscript cannot exceed subscript. It could be equal, but it cannot go beyond that. So previously we had P 10 4 is equal to P 6 1 plus P 6 2 plus P 6 3 plus P 6 4, right? That was all fine because 4 is less than 6. Okay. How about P 10 7? That is equal to P 3 1 plus P 3 2 plus P 3 3. So it does not go up all the way up to 7, but it goes all the way up to uh, 10 minus 7. So I think this should be not x, but minimum of x and n minus x, I think. Which one is, whichever is smaller, alright? So n minus x here is 6 and x is 4, so minimum of that 4. Here n minus x is 3 and x is 7, so we go to take the minimum, alright? Okay, so, okay, there we go, okay. It's minimum, okay? Yeah. We got it, alright? So, yeah, don't, we incorporated this condition by using minimum here. So, yeah, forget about this condition, okay? Because it's incorporated right here as minimum, okay? Very good. Alright. You want to take a break, okay? So, oh, gives me a headache. Yeah, now it's correct. Whew. Okay, let's take a break. Whew. Okay. So we corrected our formula, so we can erase this now. And one thing to keep in mind, okay, P n n is equal to P n 1 is equal to 1, okay? Uh, because how many ways are there to express n in terms of addition, summation of n numbers? Only one way, just 1 plus 1 n times, okay? So, and how many ways are there to express n in terms of one number, summation of one number? That's just n, okay? Only one way to do so, okay? So it kind of like the combinate, I mean the combinator is the Pascal's triangle. If one left flank, one right flank, right? So yeah, it's there's some similarity there. Okay, this we call a partition triangle. Okay. Alright. So yeah, uh, so this becomes 3. Is P of 3 3? Yes, yes. 3, 1 plus 2, 1 plus 1 plus 1. Okay, okay. Whew. Yeah, this is too easy, right? But let's leave it. Okay. P4. P4, 1 plus. Let me save my voice, okay? So. And this guy. P2, 1 plus P2, 2. This guy. Subtract, yeah, it's just P1. 1. Okay. Okay. P5. P 5 1 plus. I'm not gonna. I'm not sure if this is gonna look like Farrell's diagram or Young's diagram. I don't know. Okay. I don't know. It may look like that, or we'll see. Okay. Yeah. So, like I said, this may not be new. All right. I don't know. I don't know whether this is new or not. All right. Because Farrell's diagram, Young's diagram, I looked at it, but I didn't quite study it. Okay. Whatever. So this is one. This is one, right? And we know this is one as well. Okay. Uh, maybe not. Okay, let's see. That's like yeah. Okay, it's not one then. Okay. Yeah, no, it's not. It's not one. Okay, sorry. This guy is one. I know that. Right. Because 5 minus 4, that's 1, right? P1 1, right? So, but this guy is not 1. It's like it's 5 divided by 2 actually. Okay, so floor thereof. So and this guy. And this guy is well, this guy is 1, and this guy is P11. Yeah. This guy is P21, which is 1. Okay, so this guy P11. Okay. Alright. We keep doing this until we see a pattern, okay? I'm not quite seeing it yet. Do you? Okay. Now we're getting to see something interesting, okay? P31, P32, P33. Alright. Wow. We want, our goal now is to design something that looks like Pascal's triangle, all right? Partition triangle or partition pyramid, okay? That's our goal, and it's taking longer than I thought, all right? But we'll be patient. This is exciting, all right? Yeah. It's just taking some time, so. I'm gonna go grab a beer, okay? So, let's just sit back and enjoy, okay? Let's enjoy the show. We're not in any rush, so. Okay. So looks like each partition has its own triangle. So it will be more like a partition pyramid, like 3 dimension. Okay, 3 dimensional object. A geometric pyramid of numbers. 3 dimension. All right. Yeah. Hopefully I don't spill this beer. Okay. Now that we have room, let's do just one more, okay? With the P7, okay? Lucky 7 to end in a positive note, all right? So there we go. Maybe it's impossible to build a triangle, all right? Like Pascal's triangle fashion, because it's quite irregular. Okay, the way it looks, yeah, it's very irregular shaped triangle. Okay, so oh well. Well, uh, so okay, we know PNN is equal to PN1, and there's one more actually. Okay, PN n minus 1. Okay, they are all ones. Okay, so that's when we stop. Okay, so because Pn n minus 1 is like P1 1, Yeah. So okay, let me write this down. So we are reducing this partition number into summation of ones, right? Yeah. In this tree, each node represents one. So if you add up all the terminal nodes in graph theory, right? If you add up all the terminal nodes, lives in a tree, that's your partition function. Okay, and each leaf terminal nodes in this tree that represent one. So if you count up all the leaves in this tree, that's your partition function. Okay, at least we have recurrence formula and we have algorithm. So yeah, we are making a good progress here. So let's take a break from mathematics. Okay, so let's just give it some narrative. generic observations. So, an algorithm in computer programming language, it's not always easy to convert that into a mathematical formula, because mathematical language is quite limited. Okay, but the other direction, from mathematical formula to computer program like algorithm, oh, that's easy. That's always easy. All right. But to convert on computer program into mathematical formula, not always easy. Okay? Alright. Now that we have recurrence relation, alright, yeah, to program this into computer program, just translate mathematical language to computer program language, that's easy. Alright? Yeah. Any competent computer programmers can do it. All right, yeah. But to convert computer programming into a mathematical formula, that's not always easy. All right, is it always possible? Maybe. If not, you can always expand mathematical language. All right, so. Yeah. At first, Mr. Alan Turing asked the right question, but he didn't quite answer it correctly. His Turing machine, it's, not a huge fan, okay? It's too primitive and, but Professor Alonso Church's lambda calculus, I think is very cool, very elegant, beautiful, right? Yeah, lambda calculus. I like that. I mean, I don't know too much about it. Kind of like recursive function, whatever. But because there's this computer program language called something like ML, based on lambda calculus, right? Yeah. That's cool. Whatever. Okay. So let's draw a tree diagram, shall we? And count up the number of leaves. All right. So instead of doing plus plus plus, we'll just use this point, like vertex in graph theory. Okay. So this is not minus. No, it's an edge. It's a graph. It's a tree. All right. It's a graph. A tree is a particular graph where there's no circle. If a graph does not contain any circle, and if there's no isolated vertex point, then it's a tree. Okay, so tree is connected, fully connected graph where there is no isolated vertex, and also there is no circle. But that's tree. Okay, in graph theory. So let's count up all these leaves. Leaf in a tree, column. Okay, so this is not connected. Okay, so leaf in a tree is a node or vertex point where it's connected, but it has only one connection. Okay. On non-leaf node in a tree has multiple, at least two connections, two edges. Okay, so let's color this tree. Okay, let's decorate this Christmas tree. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 15. If 7 is partition 15, do I have my cell phone with me? I do. Let's verify this and then we take a break, okay? So. Mm-hmm. It is. Yeah. We'll take a break, okay? Yeah. Very cool. It's not as elegant as Pascal's triangle, right? But it works, okay? And we'll think about a way to construct something that looks like Pascal's triangle, okay? Because if you have a recurrence relationship, recurrence formula, then there's a good chance you can build a pyramid or triangle like Pascal's triangle, okay? Perhaps not always, I don't know, okay? But there's good chance, okay? So. All right, we'll take a break. Let's take 5 minutes, okay? Yeah. Very good. We're making progress. Okay. So all the excitement of this brand new discovery has cooled down, so my hands are no longer shaking. That's good. I mean, we don't know whether this is brand new discovery or not, but at least it's new to me. I don't know about you. Maybe you're a mathematician and you've seen this before, maybe. I don't know. But at least it's new to me, okay? And it could be rediscovery, but at least it's brand new to me. And we did it ourselves without resorting to what other people's work, right? So just pat on the back, right? Yeah. It's too close. I want some space. This guy's way too close to me. Okay. I want some space here. Oh, oh, oh. I knew this would happen one day. Just slap on the wrist, slap on the head, whatever. But what did I do wrong though? What, not proving that formula? Nah, we don't need to prove that formula. We know it's correct. We don't have time, okay, so. Okay. So, triangle, maybe we cannot build a triangle out of this, okay, because it's too irregular, alright? It's a tree, okay? And we'll think about it, alright? So, okay, we'll think about it. We'll take a break from this. I mean, are you computer science major? I am. I was, and I took this fantastic artificial intelligence class in University of Wisconsin, and it was taught by a PhD candidate during the summer semester. Okay, and it was one of my favorite classes of all time. Okay, and I can't remember minimax algorithm. All right. I think it was in artificial intelligence class. As far as I recall, but it's been like 2 decades almost since I took that class. Okay, minimax algorithm, because it kind of reminded me because we used minimum for the upper limit of sigma in our recurrence relationship, right? Recurrence formula, right? Yeah, we call it particle. I mean, not particle. Partition recurrence formula. All right. There are a lot, but we just call it at that. Okay, so and it used minimum function, right? And minimum function is quite. It's not differentiable continuous function, but it's more discrete function, right? It's not continuous function, so I guess that's why we are dealing with tree. Tree graph theory is part of a branch of discrete mathematics. Combinatorics, number theory, primes, they're all discrete mathematics. They are not part of calculus, this continuous function, smooth function. It's not, it's discrete mathematics, okay? Like Heaviside step function, I was kind of surprised that some of the prime number theory papers I read, yeah, they use Heaviside function. Okay, that was cool. Okay, step function. Yeah. Anyways, let me put just one more layer. All right. So yeah, because we're using minimum function, that's why it's kind of become irregular here in this tree. minimum function, maximum function, they are discrete function, they are not differentiable continuous function, okay? So and also three, graph theory is also discrete mathematics. Okay? You have edges, nodes, okay? Yeah. So discrete function, minimum function, and graph theory, discrete mathematics, they kind of go together. Okay, that's fine. But it's kind of lopsided triangle, upside down triangle, right? It's not symmetric. Okay. So it's not exactly triangle. Well, it kind of is, but not always. So maybe partition triangle doesn't exist. But what we have here is a partition tree, partition graph, right? I'm not disappointed, just that triangle is not the, perhaps it's not the right geometric object to describe partition function. Was then what's the right geometric object to describe partition function? Yeah, tree, graph, right? Yeah, Euler Cauchy they did study graph theory, okay, and Cauchy he's the founder of group theory. It's not Abel and Galois, no, it's Cauchy, okay. So when Abel and Galois wrote their papers, they did present to Cauchy, but by then Cauchy was way up there, so he didn't quite read their papers because Abel Galois bottom, these small young people, right? So Cauchy didn't have time to look at their paper. Okay? We cannot blame Cauchy for it, right? He was just busy. Established and very old. But when Cauchy was young, he was at the bottom level, okay? He was studying like polyhedron or whatever, okay? Yeah, this graph theory, yeah, he did study that too, okay? All these big established, I mean, not all, but many big established figures, many of them have had humble beginnings. Okay? They just rose through the ranks by patience, just like Jesus said. Jesus said, "Yeah, people who bear the tree who bear fruit is very patient trees." Okay, yeah, Jesus did say that. We love Jesus. We love Mr. Jesus. We admire Mr. Jesus. Okay, and personally, I do believe He's Son of God. I think so. But do I always agree with Mr. Jesus? No, not always. Okay. So okay, maybe triangle is not the best geometric object, but tree is to express partition function. Okay. Okay. So we came up with a brand new algorithm, and I mean, at least for me, to me, it's brand new. Okay. Recurrence formula. All right. Okay. I mean, last year I did come up with a couple of recurrence formula for partition function, but yeah, this is something new to me. It's different from what I found or rediscovered last year. Okay, so I'm very satisfied today. We got something done here. Okay, so although it may not be new, it doesn't matter. All right, we had fun, excitement of discovery. Yeah, there is some benefit of doing mathematics. Okay, so last year I discovered a couple of recurrence formula for partition function, and later on I did look it up, Oasis, okay, some other mathematical journals about partition function, and some of them turned out to be a rediscovery, others improvement, okay, or perhaps brand new, because I couldn't find the same thing. That does not mean it's not rediscovery, but still, okay, so it doesn't matter. Was I disappointed? Maybe just a little bit, but not much. Okay. Oh yeah, I appreciate other mathematicians. They did fantastic jobs. They're still doing fantastic job. Okay. Yeah, they're cool. Okay, I like them. All right. Other mathematicians. I do. So what's our next step? And there are some couple of techniques that can convert a recurrence formula into closed form formula. Yeah, there are some techniques for that in mathematics. Okay, but that's quite technical. Okay, so I know they exist. I just glossed over it, but I didn't quite study in depth because oh, it was too technical. Okay, so because my mathematics is very short and shallow, right? But I know, yeah, there are some techniques to convert recurrence relationship into closed form formula. Okay, yeah, but I didn't study it in depth. I just glossed over it. All right, we take 10 minutes break, 5 to 10 minutes break, and then we think about closed form formula for this partition function. Okay, right. Let's take 10 minutes. Okay, so I need some vocal rest. So see you soon. Okay.